Good evening and welcome to the 2022 Michio Yanai Distinguished Lecture. My name is Suzanne Paulson and I am the chair of the Department of Atmospheric and Oceanic Sciences. And I am so pleased to be able to welcome you to the first of these events since 2019. Such a relief. Thank you. This is an incredibly special lecture, and we've been doing these since 2014. The Michio Yanai Distinguished Lecture was established through a generous gift from Yoko Yanai in loving memory of her husband, Michio Yanai, who was our colleague and an expert in tropical meteorology, professor at UCLA from 1970 until 2010. The lecture has grown tremendously since its inception, and it has made such an impact on the department and on our community, enabling us to bring exceptional speakers from all over the world to engage with our faculty and our students and our researchers and also our friends and community. Thank you. Private support, like gifts from Yoko Yanai, have become increasingly critical to maintaining UCLA's excellence and providing innovative opportunities for our faculty and students. And we are so honored that Yoko chose to establish this endowed lecture at UCLA, and incredibly grateful to the Yanai family for continuing that support. This would usually be the point in my remarks where I would pause and ask you to give a round of applause to Yoko Yanai, but I am saddened to share with you that this member of our Bruin family passed away in January of this year. Yoko's legacy through this endowment will be felt in perpetuity, and we will miss her very much. We are thankful that we do have her son, Satoshi, and his wife, Joanne, joining us for this evening. And I would now like to invite Satoshi to share a few words on behalf of his family.
Thank you very much. So one thing I can say for certain is that no one came here to listen to me speak tonight, so I'm going to keep this very brief. First of all, I want to thank UCLA and the organizers of this event for continuing to keep this lecture series going, devoting the time and energy to persevere with it throughout the pandemic. We did have a lovely virtual event last year, but I'm really grateful that we're able to gather here again in person. So, as many of you know, and as was just mentioned, the Yanai Distinguished Lecture was established in part to honor the legacy of my father, Michio Yanai, a longtime member of the Department of Atmospheric and Oceanic Sciences here at UCLA. As you just heard, what some of you may not know is that the driving force in the creation and continuation of this lecture series had been my mother, Yoko Yanai, who, as you just heard, passed away earlier this year. So this is the first lecture to take place since her untimely passing. And I know how important it was to her to have partnered with UCLA in funding the series as a way to honor my father's legacy. And as sad as it is that she cannot be here today, I can only imagine how gratified she would be that this series continues to thrive and that you are all here tonight. And so for myself and on behalf of my family and for the memory of my parents, I certainly hope to attend and support many more of these lectures in the years to come. Thank you all very much.
Thank you so much, Satoshi. And now I would like to invite Roger Wakamoto, the Vice Chancellor for Research and Creative Activities, to introduce our speaker. Roger was a member of the Atmospheric and Oceanic Sciences faculty from 1983 to 2005, and he was its chair from 1996 to 2000. And then after going off and doing some remarkable things, he came back to become our Vice Chancellor. So we are particularly delighted to have him here this evening to introduce our speaker, Bjorn Stevens.
Well, thank you, Suzanne, and for those kind remarks. I'm glad to see Satoshi again. We'll talk a little bit later. So I guess this is the time when I actually take my Vice Chancellor hat off because I feel like I'm now back in atmospheric sciences. And as I always joke with Miguel Garcia Garibay, now I report to him because he's the Dean of the Physical Sciences. It's just a huge honor to be here, and it's really for two reasons. One is to be able to introduce Bjorn Stevens, but the other reason is because of Michiu Yanai. Michiu and I were very close colleagues for 22 years before I left the campus, and I can't tell you how many times he and I would talk during the day, late at night, etc. So he's always in my memory. And of course, Yoko Yanai, who we've got to know very well in all the years that I was here. In fact, I do remember, even though it was a while back, that Michiu and Yoko hosted my wife Jean and I at their house for a dinner. Really, just like a couple weeks after we first arrived here at UCLA as for me as an assistant professor, and I always fondly remembered that because it was just sort of reaffirmed that UCLA was the place I wanted to be. So back to Bjorn Stevens. Bjorn, I've had the pleasure, really, of watching your career grow from an assistant professor to really an international renowned scientist. And there's been a great deal of satisfaction in watching that. Of course, I always say, though, his career started at UCLA with a nod to Colorado State University, where he was a graduate student, but I really think his foundations were at UCLA. BS and MS degree from Iowa State University, PhD from Colorado State University in 1996. He was an NCAR postdoctoral fellow, assistant through full professor at UCLA before he departed in 2008. It was just a couple of years after I departed. So we both took that plunge and decided to leave UCLA. But I've joked with him, I came back, and so now he should consider coming back too. He's now the director of the Max Planck Institute for Meteorology at Hamburg, Germany. I think in terms of a one-sentence statement about what Bjorn is interested in, he's interested in how the atmospheric water vapor and clouds shape climate globally and regionally. I think that succinctly describes Bjorn's career. His list of honors are really incredibly long, and I'm not going to list them here, but they're all very well deserved. I wanted to share, though, one story, because Bjorn's not going to get away without me telling one story, and that is when we were recruiting him to UCLA. I was chair of the department, and I remember the department just all telling me, we got to get Bjorn, we got to get Bjorn. I remember Jim McWilliams was in my office several times saying, we've got to convince Bjorn to come to UCLA. So I remember I was going to NCAR, the National Center for Atmospheric Research, for a meeting, and I emailed Bjorn because at that time he was a postdoc. And he said, look, Bjorn, why don't we just get together in Boulder? I'd like to talk to you more about coming to UCLA. He said, great. So I don't know if you all know Boulder, Colorado, but what else is the rendezvous place but Pearl Street Mall? It's a really sort of get together place. And Bjorn suggested, I can't remember where, let's get together on 6, I think, at Pearl Street Mall. It was winter. It was really cold, I remember. And it was dark. That's another reason why I remember it was winter. So I was waiting for Bjorn. And then I noticed out of the corner of the eye this kind of dark figure with blue jeans and had a hoodie on that was so far over the head I couldn't see the face. And as the person started approaching, I was just on the verge of saying, just don't annoy me, just get away from me. You know, don't bother me, I have an important meeting here. And except just before I started to wave this person off, I heard this, oh, hi, Roger. I was going, oh, great. And so I think, oh, man, I just almost undercut the entire search by telling this guy to just get away from me. I will also say that Bjorn, and Bjorn will admit to this, he was on the far end of the spectrum of casually dressed. I'll just say that. He's really picked up his act since he's gotten these high-level positions. So I will close by saying that I think with all of us, we're very proud of Bjorn's accomplishments and so glad that he could come back here and not only honor us by his presence, but also honor the memory of Michiu Yanai. So with that, Bjorn, I'll just turn it over to you.
Thank you very much, Roger and Suzanne and everyone, for making it so pleasant to come back here. I'm going to just begin, if there's some lights up here in a sec. And bear with me at the beginning, because maybe it will be a little bit of an unconventional beginning. So this is where I was a month ago. And it's a picture out of I was flying around in a DC-3. DC-3 is an interesting plane because if you go to Santa Monica Airport, they have the DC-3 there as the sort of monument. They were built by the Douglas Commercial, by the Douglas Commercial Company, which later became McDonnell Douglas. In the 30s, the plane I was flying on was built only a couple of years after the birth of Michio Yanai. They started around in 1936, and he was born in 1934. And this is a picture from that DC-3. And it's a picture of the archipelago, which is called Svalbard, which is in the very north of the Atlantic Ocean, kind of forming a border with Greenland. And this is April 1st, and what you can see is the wonderful ways in which water imprints itself on the atmosphere. So we have clouds here, which we refer to sometimes as atmospheric convection. And so it's the cold air is flowing over the ice, and it's causing clouds to form. And then you see the ice of the Spitsbergen Island in Svalbard, and you here see the wonderful patterns of the sea ice. So you see water in all of its phases there. And if you back up a little bit and look at that same day when we were flying around, what you can see here, this is Greenland, just to orient you, and you can kind of see Alaska going around here. And this is Svalbard, and this island is called Spitsbergen, and this is the Fram Strait between Svalbard and Greenland. And it's the Fram Strait because the ship, the Fram, I think it was, I don't know his name, Fridtjof Nansen, who had the ship that was bound into the Arctic ice 100 years ago. And the pattern of the ice, you get frozen in and you come around here. So here we are in April, 1st of April. I was flying back and forth across here. And I was fascinated by how the Arctic works. Normally, most of my work is in the tropics, in the deep tropics. And one of the things that you see in the Arctic, I'll put the North Pole up there for you. That's where the North Pole is. All the satellite images kind of get bound together. There's the North Pole. So we're pretty close. This is 78 degrees north. This is about 80 degrees north, and the North Pole is there. And what happens on the North Pole in the polar night, the air loses a lot of energy to space by radiation, just like you would do in the desert on a dry night. And it gets very cold. And it forms a dome of cold air here. And that creates a pressure gradient. So you have heavy, dense cold air here in the polar areas and lighter air here. And that drives the circulation, which goes counterclockwise like that, or clockwise, sorry, I can't get my clocks right. So it will drive a circulation like this. And what happens when you have a circulation going around this, we call this easterlies. Winds we name in the same way as we name people based on where they come from. You know, your last name refers to where you came from. And the winds, they're called easterlies if they came from the east. So you have these polar easterlies. And as they flow around, what happens is they tend to diverge outward. And so you get a low-level flow near the surface, which moves away from the pole and then into the lower latitudes. So you see a divergent flow here. And it turns out that the wind and where it comes from and where it goes to imprints itself remarkably on the atmosphere. So here you could look at that a little bit closer. We'll just zoom in. And again, this is Svalbard. This is Greenland. This is the Fram Strait. Here you can see it's a satellite image, which is a fairly high resolution. This is a ice sheet that's extending off Greenland, and this is sea ice here that's breaking up, and here you see the ocean and the clouds. And the wind that's coming around this circle and is diverging over the ice imprints itself in different ways. So here you see when the flow goes over the ocean, you see these wonderful streets of clouds forming. So sometimes we call these cold air outbreaks because this cold polar air, minus 20, minus 30, is flowing out over the ice and over the warm ocean. And then it forms atmospheric convection in these wind-aligned streets here, and they get larger. The wind that goes over here, Svalbard, the island, the mountains there are maybe 1,000 meters, 3,000 feet. And so when it comes over here, this is a form of the Santa Anas. You can actually think of it, when you have Santa Anas here, you have very cold air over the Great Basin. It does that same dance around the cold air, and then it gets forced over the San Gabriels, and then down. And that's what happens here. You see there's no clouds here. And that's because you have the air is being forced downward, and it makes it anomalously warm and dry, like the Santa Anas. And that stops the clouds from forming here. So the air that goes over the mountain does one thing, it has no clouds. The air that goes over the water forms this rich pattern of convection. And the air that comes out over the ice here seems to do very little. It sort of stays the same. So you see lots of clouds here, but they're bound to the ice edge. No clouds here because the air was forced down over the mountain, and no clouds here because things haven't really changed. And so we're flying there, and I will show you another picture. That's where we're flying. We left here. This is a city called Longyearbyen, and we flew out of Longyearbyen in this DC-3, and we just went back and forth, looking down at these clouds, trying to understand how they work. And what we did we would drop sondes, what we call radiosondes. Well, not radiosondes, drop sondes. So you drop them out of the plane. They have a little parachute, and they have a GPS receiver, and they measure temperature and humidity and winds. And you can kind of get a sense of how the atmosphere changes as you move across here. And this is a picture of it. So here, this is the ice edge, and this is near the island. And what these show, this is height here. So this 2,000 means it's 2,000 meters. And this is temperature here on the x-axis. And this is over the ice, and this is over the cloud-free region on the island. And what you see if you look at all of these at about 2,000 meters, the air that's relatively high up, 2,000 meters, 6,000 feet or so, the temperatures are all around minus 25. It's the same up here. But what's different is near the surface. And so when the air flows over the ice, you see it is this very cold Arctic air, minus 25 degrees Celsius, which I don't know in Fahrenheit is maybe minus 5 or 10 or something like that. So it's pretty cold. And then as you go over here, over the water, what you see is a layer that forms here. Here it's very shallow. We call that an inversion layer where normally the temperature decreases with height, and here the temperature increases with height. And you notice that too. I don't know if you go on a summer day, if you go hiking in the Santa Monica Mountains, sometimes you get above this inversion layer, and you'll have very cool air down below from the stratocumulus, the low-lying June gloom, and you get up above that cloud layer, and the air gets very warm. So the moisture in the cool air gets trapped near the surface here in a very shallow layer. But when it goes over the water, what you find is that the water is relatively warm. It's about minus 2 degrees compared to minus 25. And it's just like this cooking pot, which it's causing huge amounts of evaporation and heat release to come off the ocean. And it deepens what we call the atmospheric boundary layer. And then the clouds form as it deepens. Bear with me. Over here, what's happening is that the air that's up here is being forced downward. And as the air gets forced downward, it's compressed. And when you compress air, it warms up, which you might notice when you pump up probably you don't spend a lot of time pumping up your bike tire, but if you do, you might notice that warmth of the compression, or if you let the air out, the cooling. And so you see this wonderful cross-section of, depending where the wind came from and where it blows, it informs how the atmosphere will look. So over the ice, I don't know if you can see here, this is the edge of the ice. This is this wonderful assemblage of puzzle pieces of fragmented ice in the broken ice sheet here. And then over here you see these streets of clouds, and they form from little gaps in the ice. But when you get over the open water, you get these long, and you can see these streets, these wind-aligned streets of ice. So depending on where the wind comes from, it looks like this and what it goes over, or it looks like this, or it looks like this. Which brings me to another point, which is another, I don't know what you would call an Angelino who moves to Los Angeles but isn't really from Los Angeles. This guy comes from Hibbing, Minnesota, but just bear with him.
Look out, kid, no matter what you did. Walk on your tiptoes, don't tie no bows. Better stay away from those that carry around a fire hose. Keep a clean nose, wash your clean clothes. You don't need a weatherman to know which way the wind blows.
I like this video. This is Subterranean Homesick Blues from Bob Dylan. It was written in 1966. He lives right above Point Doom, so that's why I called him a transplanted Angelino. But in this video, he throws these cards out, and he stops right there with that famous line, "You don't need a weatherman to know which way the wind blows." And I just wanted to add something, and this will get to Michio, is if you know which way the wind blows, and that was that long story I gave before. If you know which way the wind blows, you don't really need a weatherman either. And you know that here. I was always amazed when I lived here as how the winds just had to change direction for a few days. And the place goes up in flames right? I mean, normally you have onshore flow, but you have a few days of strong offshore flow, and Southern California starts burning. And so the direction the wind blows has a huge influence on how the weather will evolve. And there's somebody who spent more than anyone else a lot of time thinking about how the wind blows and what that does to the weather. And that was this guy here, Michio Yanai. And Satoshi, I don't know which one you are. You're here, yeah. This is 1970 when Michio Yanai, he actually, so he came around 1970 to UCLA, and he spent his career trying to understand how the wind blows and how that influences the weather. And we'll get to the lecture that you thought you were going to hear eventually. Don't wonder. One of the things he did was he made he made his early fame in understanding the sort of fortuitous fallout of these nuclear explosions that happened in the Marshall Islands in the 1950s. So in the 1950s, the United States was developing its weapons program, and we were bombing the hell out of what's called the Marshall Islands here. So the planes would drop bombs mostly, or they would bomb them, and they would let them off at the ground at the surface, but there were atmospheric tests. And this was from Operation Red Wing, and this is the Apache. I mean, I think of that, we bombed the hell out of the Marshall Islands, and we named it after Native Americans. So this is the Apache explosion. And this explosion here shows the picture. What they did was they would set up stations. And remember I said from that DC-3 we were dropping these things out of the airplane to measure the temperature and the winds and things like this. Here they would put them on balloons, and they would make those same measurements on balloons, and it would carry it up through the atmosphere. And if you could make a circle of balloons like this, you could kind of get a sense of what the atmosphere was doing as a function of the winds. And Michio recognized this, and he said, we can use these measurements of the atmosphere to try to understand something about how the atmosphere works. So he found a very productive way to use the measurements that they had to make for the atomic bomb, but he found a positive use of these measurements. And he used it to study not little clouds like this, but much deeper clouds that would form, which drive the atmospheric circulation. And so what he was interested in was how tropical convection, deep rainstorms that reach up through the atmosphere many kilometers, how they work. Why do they form? How do they form? What do they do? And they're important because the way the atmosphere works, it's very simple. The atmosphere, it's a greenhouse atmosphere, which means it loses energy to space and it loses energy to the surface. And so if the atmosphere is losing energy, it has to come back from somewhere, right? So the atmosphere is constantly radiating energy to space and to the surface. So you have to put it back. And the way the Earth puts that back is in the form of deep convective storms, which condense water, which we know is rain. And these storms let out a tremendous amount of energy. So every second, I calculated this, someone else can do it, and maybe they'll find a factor of 2 or 5 error, but roughly every second, these rainstorms in the tropics, they release as much energy as 5. This was a 2 megaton, 1.9 megaton explosion. Every second, it's like 5 of these are going off in the tropical atmosphere. And their job is to take the heat that's accumulated from the sunlight in the ocean and transport that into the atmosphere to replenish the energy that the atmosphere loses to the surface and to space. And these are the things that Michio was interested in, because this energy source in the atmosphere, you can imagine, has a big influence on the winds. And as it turns out, the winds have a big influence on this energy source, as we were saying. And you can see this a little bit what I mean here. This is the Atlantic now. We're going to the tropics and the Atlantic. And this is the coast of Brazil. And you can see the Amazon here. You actually can see the tributaries to the Amazon. It's fascinating, the satellite pictures on how the river path is cloud-free, and small clouds are like dusting of powder sugar along the Amazon here. But I want to draw your attention to this sort of band of clouds here. And if you look at this band, it looks a bit like a squiggle. And if you blow up on that squiggle right there, that's what you see. So these are these explosive rain showers that are forming over what we call this intertropical convergence zone, when air, moist, warm air, converges together at low levels and forms very deep storms. Roger would study these storms, Roger Wakamoto, all the time when they would form over Oklahoma and western Colorado, when you would see this meeting of very humid air masses. And you would have this, if you count them, there's about 50 of these little cells here. Big storms making lots of rain. And they're putting heat in the atmosphere. So they're heat sources. They're heating the atmosphere is losing energy uniformly, and it's being put back somewhat stochastically in small places. So it's concentrated, this heating is concentrated in space and time. And this is, here I was flying on a different plane, not a DC-3, it was a Gulfstream. And these little, this is a picture out the plane window of these same clouds here a few hours later. And the point I wanted to make is that these towering clouds, they reach up to 13, 14, 15, sometimes up to 20 kilometers in the atmosphere, are the sort of atomic bombs which are putting the energy back into the atmosphere that the atmosphere is otherwise losing. And they're concentrated in space and time. And so the question is, why do they form there? And what do they do when they form there? And these are questions Michio was quite interested in. One of the things he was very famous for is something called the Yanai wave. And what he used those measurements to show around these atolls and the blues, he could track how the winds changed. And this is from a famous paper that he wrote with Maruyama. And what it shows here, this is height. So this is kilometers in the atmosphere. So the balloons went high, 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 and you could measure the wind. And these little wind barbs are the wind direction at the different heights, and this is different times. So this is the 15th of April, 1958, and the 30th of April. And what he did was here, he colored everywhere where the wind had a little bit, it came from the south. So if you look at the wind barbs that show where's the wind come from. So if you look here, it's coming from the sort of 7 o'clock direction. It's coming from the lower left and going up to the upper right. Whereas when you're here, the winds are going this way. And so what he found was a very large-scale oscillation in the wind in the upper atmosphere, which is called the Yanai wave. Sometimes it's called the Yanai-Maruyama wave, but I always learned of this as the Yanai wave. The technicians would call it a mixed Rossby gravity wave, but it was the Yanai wave. There's very few people in our field who have a large-scale pattern of circulation changes named after them, and Michio was one of them. And he showed that these things are probably caused by this concentration of storms that happen in small areas over the equator. And they carry energy up into the stratosphere, which affects the direction of the winds back and forth in the stratosphere. So the convection, these clouds, these deep thunderstorms, affect the wind, but the wind affects the convection. And this is what he showed in another paper here. So this was in 1961. And here he was trying to understand why tropical cyclones form. So what you would look at is he would find in the tropics, what this shows is, it's a line here, this is longitude. So this is the date line, 180 east, and this is going further west. And this is latitude, and here's the equator. And all you should really be able to see in this figure is that the solid lines have a little bit of a kink. So you probably can see that. You see that if you follow one of these lines, it's following the motion of the air at about 2 kilometers of height, and it has a little bit of a kink in it. And when it had a little bit of a kink, he showed how these kinks were quite important for forming tropical cyclones. So when do tropical cyclones form? And his argument that it was an instability in the flow, in the large-scale pattern of the winds. So again, what I want you to understand from this is that what Michio Yanai was very interested in was how the winds affect the storms and how the storms affect the winds. So two sides of the coin. It wasn't if you know which way the wind blows, you will know the weather, because you need to know the weather to know which way the wind blows. And Michio looked at both sides of these, and apparently Bob Dylan wasn't paying attention. And here's an example that came out much later, is if you do this experiment a little bit further and you say, let's change where the storms form, and ask how it changes where the wind blows. This is an example here. You see the Pacific Ocean. We're sitting somewhere here. And this little speckled area, we can play the thought experiment of what if the ocean was a bit warmer there? And if the ocean's a bit warmer there, then you kind of collect the storms that are, these atomic blasts, so to speak, that are transferring energy from the ocean into the atmosphere. You're concentrating them here. And this causes a large-scale disturbance in the wind, which has a global influence. And this global influence looks like what we call a wave train, this pattern of alternating high and low pressures. And this wave train goes from high to low, which changes the way the winds blow in the northern Pacific. And later studies have shown that if you change where the convection forms here, it affects things as far away as fisheries in the northeast Pacific. So if you look at the weight of sockeye salmon or all of these other species of fish which swim up the rivers here in Canada, they're associated with shifts in the convection that happen in the deep tropical Pacific. So knowing how the weather develops tells you not only how the winds blow there, but influences how the winds blow over the whole globe. This is a paper. This is you, isn't it? Yeah, so this is Hui Su and David Nealon, who's taller than the rest of you in the back because of his chair. This is a paper out of his group, and what they were looking at was when you have precipitation anomalies with El Nino, how this not only affects this extratropical influences, but if it's raining more here in the eastern Pacific, how that dries out the Amazon or the Atlantic or the Indian Ocean. So this ability of changing where the storms form, how that affects winds globally. So I'm going to pause here and then get to my talk. And what I wanted you to get out of that introduction was that knowing which way the winds blow can be pretty informative. And as a backdrop, I was trying to convince you that the way the atmosphere works is it loses energy to space and it loses energy to the surface, so it's always chilling. The atmosphere is always losing energy, and it has to get back, and it gets back by making rain. So the reason we have rain is because the atmosphere is trying to be warmed up, because otherwise it becomes much colder than the surface. The surface evaporates vapor, and that condenses in the atmosphere, and the heating from that balances the loss of energy to space. And this heating just doesn't happen everywhere uniformly. It happens in particular places, and where it happens sculpts and shapes the entire pattern of winds over the whole planet. So there's this subtle interplay between the winds and the weather. Now you can say to understand global warming, you don't need to know anything about that. So to understand global warming, you didn't, I'm sorry to say, need Michio Yanai. What he did wouldn't help you. You just didn't need to know that. But if you want to understand what warming means for weather, if you want to understand how the weather will change, so where's Alex? Alex here studies fire weather, Alex Hall, and he's very interested in why sometimes we have many more fires and other times we don't have many more fires. That's what I would call weather. So how often do we have Santa Anas in a year, and how will that change? That's about as close as you get to weather. If you want to understand weather, then you most certainly do need Michio Yanai to understand this interplay of the winds with the weather. Which brings me to my advertised talk. Today I want to talk to you about what we don't know about global warming. And maybe you can guess the answer given the introduction. We don't really know what's going to happen to the rains. Small shifts in the rain lead to shifts in the weather. And if we're really interested in understanding how the weather is going to change, how often we're going to have differences in Santa Anas, how often we're going to have heat waves like we had in I don't remember last year, that Northwest, this super heat wave, how often we had floods like we saw in the previous summer. If you want to understand those sorts of things, you have to understand this interplay between the winds and the storms. And what I would say, and this is said a bit bluntly, because we do know roughly where it rains. We know it rains near the equator. We know why it forms in the western part of the ocean, but with a specificity that we need to know it to plan for a warmer world. You could say that we don't really know where it will rain and how this will change. And if you look at our most sophisticated models of the climate system, the ones which are perfectly adequate for telling us the world is warming, there's no doubt about that. What we find is they're not very informative in terms of telling us about how it rains, the storms that Michio was interested in. They will rain in the wrong place, they rain at the wrong time, they rain with the wrong intensity, and they rain with the wrong structure. Every possible way in which they could be wrong, they are wrong. Here's an example. This is the models that are used in the international assessments of climate change. So these are called, they have a code name called CMIP. So it's Coupled Model Intercomparison Project. And what we've done here is in the last version of this, which went into the last round of documents for this IPCC, we took those models and we just asked, what is the systematic error? So any model might have a bit of random error. It makes it the rain form too far north or too far south. But ideally, the systematic error wouldn't be large, so that the differences among models would average out, and you would have a reasonably good picture of where it rains. And what this shows you is that if you do that, the systematic error makes the tropics too wet here and here and here, and too dry on the equator. If you look at Brazil, it's much too dry, and I'm going to explain much too dry. The average rainfall on the Earth is about 3 millimeters a day. And 3 millimeters a day is this color here or this color here. So these are errors of the magnitude. In the tropics, it rains much more. So here, the tropics, the rainfall rates can be anywhere from 10 to 15, 17 millimeters a day. So depending on how you count, these are sort of 100% errors, or they're 20 or 30% errors. But they're systematic across all models. We rain too far poleward in this main rain band here. There's not enough rain over the Western Pacific. The Amazon is dry. So because of this, the winds blow not quite like you would like the winds to blow. So if you don't know where it rains now, it's hard to say how the rain is going to change in the future. Now you could say the models are getting better. The reality, of course, is the models we use for these international assessments aren't getting better. And we've been doing it for 30 or 40 years, and they've had these errors for 30 or 40 years, and I'm going to explain why I think that is in a second. The other thing about these models is some people say, well, actually, they're a little bit better, but the people who make the models, and our lab is one of the labs that have been making these models for a long time, we know the answer. You know, we know what the answer should look like. And so we go through this process of making the models where we keep the changes that make the answer look better, and we throw away the changes that make the answer look worse. Just a rational sort of thing to do if you're trying to make a model that looks like the Earth. But we go through this process of fitting to the data, and we're still left with these very large errors in how the rain forms. But if you went to the IPCC and you asked how the rain changes, you would get this figure. So this was in this report that came out last September or something like this. It's called the Sixth Assessment Report of the Intergovernmental Panel on Climate Change, which many people here have been involved with in varying degrees, myself included. So please don't interpret this as bashing this panel. I'm just trying to present the knowledge here as it's presented. And they give you a figure like this. They say this is the best estimate of the rainfall changes. So if you looked at that, you would say, okay, the tropics are going to get wet, the subtropics are going to get dry. If you live in the Caribbean, it's a big problem because it's going to get really dry. Brown is dry here. That means sort of like a 70%, the dark brown, change in rainfall. So you're going to lose a lot of rain. The Sahara is going to get really wet. And maybe it's not so bad to be a Saudi, you know, from that plot. So this figure was put in the document in a very high level. It was the summary for policymakers, the most high level document that they produce, figure 5. They showed this figure. What they didn't really want to advertise was that figure was an average of many models. And if you look across the models and you look at any different part of the globe, you could create different figures. And this they show laid deep in the third level document in the report in figure 442, where they say, well, if we take 50 models, and we take the 5 or so which at any point which are wettest, or take the 5 or so which are driest, you can kind of get. Do you guys know Arlo Guthrie, that song? You can get anything you want at Alice's restaurant. That's what I think of in this figure. So if you live here, you would get a prediction that tells you that you could find models, not just one, but several models, which would tell you that the Sahara is going to increase the rainfall by 200%. But you could also find ones which would tell you that it's going to be drying by 200%. Or maybe 150%. And there's very little area, maybe just here in this band here, where the models all tend to produce the same thing. If you're in Svalbard, you're okay. In the very high latitudes, the models tend to all show that the high latitudes are warming and the high latitudes are going to be wetter. And there's good reasons why we think that's the case. But if you live in this tropical part of the world, this half of the world that's the tropics, and the weather doesn't change. Weather there is rain, it's fire, it's dry. The thing that you care about, you don't really know very much about. And of course, this matters. So how does it matter? So this is Munich Re, this is the Munich Reinsurance. They are one of the biggest reinsurers for natural hazards, and they make a map every year about the natural catastrophes. And this is last year's. And in 2021, they estimated 210 billion of losses. That's a lot of money, 210 billion. It's even more than Roger can raise through this, so only a bit. But 210 billion of losses, 8,000 fatalities. And here they kind of show where all the events that went into that number came from. These were probably wildfires here, the brown, but they didn't get a special call out because it wasn't a big thing. The big things we see are Hurricane Ida, where you had 114 fatalities and lost 65 billion. Winter storm, this big winter storm that went down into the southern states, 30 billions of losses. That tornado outbreak, which is a streak of tornadoes. Did you actually go survey those? So Roger was quite famous because he would go after big tornadic outbreaks. He would go and survey the damage to learn about how the tornadoes worked. That was 5 billion. Here in the sort of the Benelux countries, Germany, Luxembourg, Belgium, it's called the Eifel region, there was giant floods which caused 54 billion in damage. Some of you might remember central China. They had these Henan floods, which were 16.5 billion. But if you look at this 210 billion, all of these are what we call hydrometeorological damages. They're from the storms that Michio, you and I would try to understand. So if we want to prepare for climate change, we have to be able to understand something about how the rain will change, and to understand that we have to know how the winds will change. So now I'm going to do a thought experiment for you. So we can play a game. This is the sort of active time. I hope you all have clickers. So what we're going to do, here's the thought experiment. 70 years of measurements. You all have 70 years of measurements. And we know that in these 70 years, the planet's warmed by 1 degree. And we all accept that 1.5 degrees is dangerous. That's kind of what we're saying. We need to limit warming to 1.5 degrees. And it sounds like I'm making fun of that. I'm not. Let's just accept that 1.5 degrees is dangerous, and I believe that's probably true. I can't reason it for you, but I don't have a problem with that statement. And we have many millennia of documented experience in all the holy books that when people behave badly, then they're penalized by drought and flood, right? So we know that also to be true. So we've been behaving poorly, and the world is getting warmer, and it's 2/3 of the way to being too warm. So we can go through the world, and we can count up how we've been penalized. That's the scientific game, right? We can say, let's break the world into pieces, and we'll show in a second, it'll be 45 pieces. We'll break the world into 45 pieces, and we'll ask ourselves, can we demonstrate that people have been behaving poorly there? And that means that there was either a trend in floods or droughts, and warming is the cause. So the IPCC asked this question. So they said, let's break the world into 45 regions, and then we'll say, in those 45 regions, can we either document a trend in floods or droughts. So that's two possibilities, 45 regions, 90 cases. And if we can document a trend, can we attribute that to warming? 70 years of data, 1 degree. This is the figure they came up with, and it's kind of a nice figure. Do you know that game Settlers of Catan? Does anybody know that board game? They have these little hexagons, so I call this the Settlers of Catan figure. And they broke the world into these little hexagons here, and so this is North America, South America. You can kind of see Africa looks a bit like a diamond, and then Australia, New Zealand, Asia. And this is the flood figure, and this is the drought figure. And what they did was they colored the tiles based on whether they could see a trend. So where the figures are green, there's good evidence of a trend. That means these regions have been, penalized by floods, and these ones have been penalized by droughts. And sometimes you're penalized by both. So if you're here in the kind of Black Sea region, you have more floods and more droughts, so they've been really bad. But then they do one other thing. They put a little asterisk on the figure, and they say that's our level of confidence that we've identified a trend, and the trend is due to warming. And they have 3 asterisks. So they say, well, there's 2 reasons we might have no confidence in the trend being from warming. One is because we have no data, and the other is because we just can't agree. 2 stars mean that we're medium confident, whatever that means, but they're kind of confident. And then 3 stars mean you're very confident. So guess how many of those 90 possibilities, you've probably seen it by now, but where we're very confident that there's a trend, and it's due to warming. 1. Here, northeastern Europe, not so far from Svalbard, where I was. And if you ask where do we have 2-star regions, I think I counted 3. Maybe I did wrong, but I only could find 3. There's a Mediterranean down here, Western North America here, that's the fires. And there's the Central North America here, which is getting wetter. So there's 3 regions where we have, after 70 years of data, where we have confidence that we can say something about how the change in the winds are blowing and the change in the weather. And in the tropics, very little confidence. And to me, this is the problem, why it matters. When you think about what's happening in the world right now and how much money is being spent in a world that's changing, and we don't really know the way in which it's changing. So this is a map which shows the fastest growing cities in the world. I think it's the top 15 or 20. It comes from the United Nations, the world's fastest growing cities based on this urbanization project. And almost all of them are in Central Africa. So you see massive urbanization happening in Africa. There's massive investment happening in Africa. The Chinese are building factories like crazy here in this northern region. So we're investing enormous amounts of money building infrastructure without really understanding what the risk is to that infrastructure from the changing weather. And I work a lot in Barbados, and this came really sharply to my mind, because when we were there, it had been dry for a few years, and they were in the impression that they had to work on dealing with drought. So they had been spending a lot of money in a country which doesn't have a lot of money, but all the rainfall that falls, I mean, their fresh water is what falls on their head and into the ground, and they pick back out of the ground. They have to use their resources wisely, and they're like, it's getting drier, and so they invested in desalinization plants. But then the year after we were there, they had like 2 or 3 years of record rain. And this was in the newspaper I found, is that this is the Barbados Water Authority's this is the Nation News in Barbados. Director of Engineering said today that repairs continue at the desalinization plant. This is February, it's the dry season. It's in the midst of the deepest of the dry season. But they had to stop work on the desalinization plant because of flooding. So it shows you the reality of the choices that you have to make in places like this. You have limited resources. Do you prepare to give yourself more fresh water, or do you protect yourself from flooding? And many of these countries can't do both. The last part on the why it matters is here in a couple slides. Is pretty often we read in the paper that as the world warms, we're really going to be in big trouble. So you hear things like the Amazon rainforest is going to die off. You've probably heard every year around Christmas we get a story about the Tools ice sheet in Antarctica. People measure it and it's about to break off the biggest ice chunk. The Guardian runs the same story every year about the ice sheets breaking off. Greenland, maybe this will collapse. There's permafrost in the north which will melt, which has huge methane reserves. The boreal forests will burn, the jet stream will shift, we'll have a permanent El Nino, the thermohaline, which takes warm water to the poles, will collapse, the monsoon will fail, and the coral reefs will bleach. And each one of these are colored by when these authors, this was a preceding National Academy Science paper, where people are kind of speculating about the worst case scenarios. And all of these, there's a certain amount of there's a certain amount of truth to them. All of these, there's a certain logic which says they could happen. Most of us don't believe most of these, but they continue to be talked about, and they would be catastrophic if they happened. And the way this paper made the case was they said, well, these things happen when it gets 1 degree warmer to 3 degrees, and these we'll call extra warming, which will make it 3 degrees warmer, and then the brown ones will go, and that will make it 5 degrees warmer, and then the red ones will go, which will make it even warmer. So we have a lot of these disaster scenarios, and we were talking a little bit about how to deal with the worst cases, because often, though, it's easy to make fun of the really speculative worst cases, but sometimes they come true. And so the thing that I wanted to point out is that all of these, or almost all of them, are hydrometeorological in character. So the balance of the ice sheets depends on how much snow falls versus how much heat is transported by the ocean. The El Nino and Southern Oscillation, these are the storm systems that David and Michio would study. The monsoon, the rainforest, Sahel, boreal forest, these are all permafrost. These are all hydrometeorological, and they're all regional, and they're all things that we have a poor understanding of. And it's gotten to the point where, again, the IPCC, this is a figure they make, I think it's a figure 8, and what they show is many graphs of how the world could change over time. And they show that in different scenarios, this is the surface temperature, and it's going up. And in different scenarios, depending on how much CO2, it goes up more, it goes up less. But on the bottom here, there's sea level rise. And this is the scary one, right? So in the report, they have, if you look at this figure here, it's kind of blowing up. The sea level rise, 1990 to 2100. It could go up 1 meter, 1.5 meters. And then they go, let's jump to 2300. And then they put this in. And they say that by 2300, sea level rise, they can't rule out 15 meters of sea level rise. That's Armageddon. 15 meters of sea level rise is the end of the world as we know it. But how can you say this as a self-respecting scientist? Because it doesn't mean it's not true. But the fact that we don't know irritates the hell out of me. Because we're scientists, and this is what we do. And we're half of the time in the community, we spend our time telling people about it's getting warmer, and somehow we're content with statements like this. And a lot of the people in the audience, and certainly the faculty, aren't content with statements like that. And the point I really want to make is there's lots of science that needs to be done because the world is changing, it is warming, and we can't even have a sensible discourse about what that means at times because of some of these unknowns. Okay, I'm at 42 minutes on my clock, so I have 6 more slides, and I'm going to show you how you could know a bit more and where Roger is going to invest his $210 billion of investment here, and why we know so little. Some of you might. This is a climate model. This is kind of how today's climate models worked. It's a bit of an older one, and the visualization doesn't make it look particularly great. But the idea of climate that we had for a long time was based on this idea that we had a very large scale. The winds, we kind of knew how the winds blow. And if we knew how the winds blow, then we just had to figure out how the storms responded. So it was more of this idea that the storms don't really influence the winds, but the winds will kind of set up the storms, or the storms are in a gentle equilibrium with the winds. And there's a famous figure here drawn by Akio Arakawa, which is a little bit modified by me, and he conceptualized this system. So this view of the climate system was born here at UCLA, more than anywhere else, I think, when you think of this idea that we can't compute everything. So let's make this hypothesis that we can calculate how the winds blow, and then we can connect the storms to them. And so Akio Arakawa put together this figure. Michio Yanai was trying to understand how that would work, and we got models like this. And what the model shows is the Earth. Here's Antarctica, here's North America. The white is deep clouds, the black is the surface, the colors are rain. And what you should see is you see a sort of train of white kind of going from west to east in the westerlies of the mid-latitudes. These are mid-latitude storms, and they carry energy from the equator where it accumulates to the pole. And in the tropics, you kind of see a band of precipitation, which is this convergence zone of these clouds. And the way the models worked was you would just more or less think of them as sort of quasi-two-dimensional layers that move air around, and they would transport heat to the pole. They did that very well. And they would assume that the convection was in equilibrium with the large scale and somehow come up with a little statistical rule of thumb about how to do that to make the rain. And this was a question that Michio worked on for a while, and it's based on this idea that somehow the convection is sort of this random, they're like molecules in a gas, they're just kind of popping away. But if you look at a real storm system, these are simulations we did over Germany, what you find is that the clouds aren't like little atoms popping up with no scale, is that they're embedded in a rich fabric of scales, and they interact with the surface on every scale. So here when you look to the south, it's the Alps, and this is a simulation, but it shows you a little bit the richness of the scales that connect the storms to the winds. So I would call these scales, and talking with Jim on this, these are the intermediate scales, which we're forced to leave out of the calculations that we've used in the past to study the climate system. And so it's not that you just see isolated clouds in a box like that figure I showed before, but you see the clouds are connected by all sorts of different scales of motion. It's a sort of beautiful thing, the way the atmosphere works, and it takes the energy from the surface. And so you say, well, what does that have to do with the story of not knowing where it rains? And here I want to make the point that when we first, and Arakawa first started making these models in the 1970s, they didn't have big computers. And they realized with a fairly small computer, we could calculate something that nobody had been able to calculate before. And that's how these quasi-two-dimensional motions would transport energy from the equator to the pole. And that's because these eddies, these storms that went from west to east, they had a scale of about 1,000 kilometers. And so you don't need many degrees of freedom to compute how they work on the planet. If you need to capture something that's as big as a few thousand kilometers across, then you don't need many points to do it. So it's a fairly large scale, and you could compute that, and then you hope that the other thing that you care about, the vertical transport of energy, you could kind of tidy that up at the end and make that work. So the climate models were built to solve this problem, how to get energy from the equator to the pole. But fundamentally, climate is a problem of transferring energy from the surface. Like we saw in the Arctic, when the cold air comes off the ice over the warm water, how you get energy from the surface into the atmosphere. And the problem we have on the Earth is, this is actually a simulated planet, the atmosphere is thin. So if you want to simulate how the vertical transport of energy happens, how those storms, like I showed before, you need a very, very, very fine computational mesh that was inconceivable when Michio began working on these problems. And if you calculate how inconceivable it was, is to get the vertical transport, you need to represent things which these clouds, that picture I had when you looked at the clouds of the tropics, they were 10 kilometers deep or 15 kilometers deep. You have to represent things which are exchanging energy over a 10-kilometer layer, not over thousands of kilometers. And the difference in scale here is 2 to the 7. That means 2 times 2 times 2 times 2 times 2 times 2 times 2, and maybe another times 2, I forget. And if you look at that, every time you increase the scale a factor of 2 to the 7, you have 4 dimensions. You have up, down, left, right, back, forth, and before and after, right? So you have 4 dimensions. And so 2 to the 7 becomes 2 to the 28. See, I could just do the 2 to the 28, 2 times 2 times 2, and then keep you to dinner. But 2 to the 28 is a big number. And so if you wanted to go from the way we originally thought, Arakawa and Michio thought of doing climate, to do it more fundamentally, you needed to be able to compute 2 to the 28 more. Does anybody know Moore's Law? He's another Californian, I guess, right? So Moore's Law says that the number of transistors will increase by how much? They double every year and a half, roughly. This is 28 doublings. So if you have to wait a year and a half for a doubling, how long do you have to wait from being able to do the Yanai Arakawa problem to doing the McWilliams problem? To the 28 a year and a half, you have to wait 42 years. When they began doing this was the mid-70s, and if you add 42 years to the mid-70s, you get to about now. And so what we're able to do now is we don't need to pretend that we know the winds and we can calculate the storms, or that we know the storms and we can calculate the winds. We can calculate them as part of the same system. So this is an example of a simulation we did where we go right through into the ocean to capture the mesoscale motions in the eddies. I'm going to zoom that, and we'll go one more time here. So this is looking at the clouds at night. This is the infrared radiation they leave off. And then the day will come up. You'll see the clouds change a little bit because we're seeing them when the sun shines, so they look a bit different. But you compare this to the way we were doing climate before, and you see we're making some progress. And it really has to do with capturing how the clouds form and how the ocean swirls. And you can even zoom in here if you look at how the ocean swirls. And here we're going down to scales of a few hundred meters. So this is, for the oceanographers, this is 500 meters where we have a zoom over the Gulf Stream. And you just see this richness of scales which are in the system. So we have tools now which can begin to look at and give us a new phenomenology of how the link between where the winds blow and how the storms form. This is looking at the Gulf Stream region. This is vorticity, so the swirl of the flow, and different colors mean the flow swirling in different directions. And so here you'll just have different measures of how much energy and motion is in the fine-scale ocean. It's this fantastic fluid that's transporting heat and energy all around the place. And we're at a point now where we can begin trying to understand how that system works because we're enriched in our phenomenology to look at that. So this capability that we have now computationally is really opening all sorts of new frontiers. I think it's one of the most exciting times in our field because the things that we really want to know, the thought is that maybe we can know them if we work together and concentrate. And so we're introducing new phenomenology in the field which we can try to learn from, because it's not enough just to have a wonderful simulation. You have to be able to convince people that you understand why it behaves how it does. But you need something to explain. And so this gives us a laboratory for virtualizing the future in ways which are much more fundamentally connected to the laws of physics that we can try to explain as scientists. So for the fields, it's a new frontier. For risk assessment, it's a new frontier. We're simulating things that do damage. So when we think of a supercell thunderstorm, which is causing enormous damage, or a hurricane, these things live on the scales that we can now simulate on a kilometer. For Earth observations, it's a new frontier because we're actually simulating the things we observe from space. The old models were built on simulating a statistic, but now we're simulating storms, events, clouds, eddies. And for computer science, I think this is one of the most exciting things, actually, is we're on this frontier where you see how important virtualization, the role virtual realities are playing in people's lives, whether that virtual reality is called the social media you find on Facebook, or it's people playing League of Nations and buying, spending hundreds and hundreds of dollars to outfit their characters. People are moving more and more into virtual worlds. And our business in the atmosphere and ocean sciences is using virtual worlds to understand the future. So this symbiosis of our field. And the thing I like the best is that it brings Michio's two sides together. So here's this picture I got from the paper by Steve Esbenson and Rob Fobel, who was at UCLA. And this shows your father here, as you probably know the picture, but as a school kid. And this is a weather vane right here, because the way the story goes, he lived for typhoons. He just wanted the typhoon to come and he could measure the winds. So this is Michio trying to understand the storm And here he's looking after the storm at rainfall maps over Japan and trying to understand what the storm did to society. And so this ability now to bring together the two sides of how storms work, how they affect the winds, to understand what climate change really means is a chance to bring together the two sides of Michio Yanai. So thanks for listening, and that's all I have to say.